In this video, we're going to look at how to optimize, in this case maximize, the area of a rectangle that is inscribed in an equilateral triangle of side length A. The rectangle will have two vertices on one of the sides of the equilateral triangle. And we want to know what are the dimensions of this rectangle going to be. So let's draw a picture first. We've got an equilateral triangle. Equilateral means the sides are congruent and the angles are also congruent. So all the angles are 60 degrees, and in this case all of the sides have length A. And inside of that triangle we are going to put a rectangle. Okay? And you can see on the bottom edge here, two of the vertices lie on one side of the triangle. And I want to know what are the dimensions of this rectangle in terms of the variable A if I maximize the area. So of course my area is going to be base times height. And we need to figure out how we can relate all of these variables to each other. So first, I think we are going to redraw this picture on an XY plane. Okay? So let's say that this is the XY plane, and here is my triangle. And I'm going to relate the rectangle to the triangle through a point where they touch. And I'm going to pick this point, a point in the first quadrant. So here's my rectangle. And here's my point in the first quadrant. I'm going to call that point XY. And this would be X, and this would be Y. So now it's actually easy to see that the base of my triangle is twice as long as X, and the height of my, that base of my rectangle, and the height of my rectangle is going to be the same thing as Y. So now I can say, okay, well now I know the area is going to be 2X times Y. In order to optimize, I'm going to need to get this down to a single variable. So I'm going to try and write my area equation just in terms of X. So now I'm going to figure out a way to get rid of the Y. Okay, if all of the sides of the triangle have length A, if this is length A, and this is on the y-axis, then this value over here must be 1/2 A on the x-axis, whereas this would be -1/2 A. And then these side lengths are length A. So if I've chosen my point XY to be a point on this side of the triangle, well, maybe I can figure out how to relate them if I write an equation for this line. So that's what I'm going to try and do. I'm going to write an equation for this line right here. Okay? So let's draw yet another picture over here. Just of that side there. So this is the line I'm looking for, and we know that this is 1/2 A, and we know the distance from here to here is A. So I need two things to write the equation of the line. I need to know a point, and I need to know a slope. So I need another point if I want a slope. So it would be really nice if I could find the y-intercept. And that's going to be easy to do because I know that this angle which is this angle in an equilateral triangle, is 60 degrees. This, of course, is a right angle, and then this must be 30 degrees. So I have a 30, 60, 90 triangle here. Okay, the hypotenuse is A, the short side is half A, and to find the long leg of a 30, 60, 90 triangle, you multiply the short leg by root 3, which means the length of this side must be root 3 over 2A. So now I know my y-intercept is root 3 over 2A. Okay, and now I can write the equation of this line. So I have a y-intercept, and I can calculate a slope using these 2 points. So my y-intercept is root 3 over 2a, and the slope is going to be rise over run, or I could just use the 2 ordered pairs, either way. So this point over here is 0 root 3 over 2a, and this point over here is 1/2 a, 0. So using my 2 points, my slope is going to be root 3 over 2a minus 0 over 0 minus 1/2 a. So the a's are going to cancel, and the halves are going to cancel down here, and I'm going to wind up with root 3 over -1, or negative root 3. So putting these 2 pieces together, my y-intercept and my slope, I can write the equation of that line, which is going to allow me to relate x to y. Y equals negative root 3x, I'm doing y equals mx plus b, plus my y-intercept, which is root 3 over 2a. And I think I am all set up to solve my maximization problem now. So going back to my area formula, the area of my rectangle is 2x times y. So area just in terms of x is going to be 2x times my y I'm going to replace with the equation for the line. So negative root 3x plus root 3 over 2a. To find extrema, in this case to find the maximum area, I need to take the derivative. First I'm going to multiply this out so that I don't have to use the product rule. So that's going to be negative 2 root 3 x squared plus, when I multiply 2x times root 3 over 2a, the 2's are going to cancel, and I'm just going to have root 3ax. So this is my area formula, and now I am ready to take the derivative. The derivative, a prime of x, equals negative 4 root 3x, negative 4 root 3x, plus root 3a. And I'm going, remember a is a constant, so when I take the derivative of root 3ax, I'm just left with root 3a. I'm going to set that equal to 0 to find my critical points, and I'm going to get negative 4 root 3x equals negative root 3a. The root 3's and the negatives are going to cancel, and then I'm going to divide by 4, and I'm going to get x is a over 4. Okay, so I should confirm that this is in fact a maximum. To figure out what type of extrema this is, I'm going to use the second derivative test because it's really easy to take the second derivative here. The second derivative of my area function is just negative 4 root 3, which is negative. So, to justify that I found a maximum, I'm going to say a prime of a over 4, my x value that I got when the derivative is 0, a prime of a over 4 is 0, and a double prime, the second derivative of a over 4, is negative, because the second derivative is always negative. So let's think about what these two pieces of information mean. There's some point on the curve where the tangent line is horizontal, and therefore the first derivative is 0, and the curve is concave down, as I've drawn here in this picture. Well, if those two things are both true, then that point must be a maximum. Therefore, a of a4, I've got a lot of a's here, is a maximum area. Okay, so I've justified that I have a maximum, and going back to what was the original question asking? The original question is asking for the dimensions of this rectangle, and we're going to write those dimensions in terms of A. So, the dimensions of the rectangle are base and height. So, dimensions are base, and we said the base is 2x, which is 2, the x value we have is a over 4, which is a over 2 when I multiply that together. And then, of course, the height of our rectangle is y, which, using our equation from our line, y equals negative root 3x plus root 3 over 2a. So let's plug the x value in there. Negative root 3 a over 2. Oops, my x value is a over 4. That would have been a big mistake, because if I realized something was wrong, I would have wound up with 0, which was not going to work. Plus, again, the x value came from way back up there, plus root 3 over 2a. So let's give those a common denominator, which is going to be 4, negative root 3a, plus, I have to multiply by 2 over 2, 2 root 3a, and that's going to give me root 3a over 4, root 3a over 4. All right, so my dimensions of my rectangle are a over 2 by root 3 over 4a, where a is the length of the side of the equilateral triangle in which my rectangle is inscribed. Equilateral triangle side length. All right, optimization in a nutshell. Hope you enjoyed it.